Section 3.4, concavity, points of inflection, and the second derivative test. So let's take a function that is continuous and differentiable. We know that in this interval, this function is increasing here and here. Look at the first derivative graph. The first derivative takes the slopes of the tangent lines on the function and plots them as coordinates of points. So you'll notice that when my slope is positive, my function f is increasing and my y values on f are positive. When f is decreasing, the slopes are negative and my y values are negative. Note at A, I have a horizontal tangent on the first derivative that corresponds to a 0 because I'm going from positive slopes to negative slopes. Notice at C, I have another horizontal tangent on f because I am going from negative slopes to positive slopes. But an interesting thing is happening on function f between A and C, and that is where the shape of the graph is going from a concave down shape to a concave up shape. Notice that at B, I have this point, which is called a point of inflection. This is where the graph of f changes from concavity, from concave down to concave up, or it could change from concave up to concave down. Let's look at how B is represented on the first derivative graph. Look at that. It has a horizontal tangent. So notice that here I have my graph of f is concave down. Notice that my y values on f prime are decreasing. And that corresponds on the second derivative to negative y values. Notice where graph f is concave up. On the first derivative graph, my y values are increasing, and on the second derivative graph, my y values are positive. Notice that at my point of inflection, we have a horizontal tangent on the first derivative graph and a 0 on the second derivative graph. Now let's look at our notation. So where f prime is positive, where my slope of my tangent line is positive, f will be increasing. So notice my f prime values are positive here and here. Function f is increasing. Where f prime is negative, where my y values on the f prime graph are negative, function f is going to be decreasing. Now let's go to the second derivative. Where f double prime, the second derivative, is positive, f prime is increasing, and f is concave up. Where the second derivative has negative y values, f prime is decreasing, and f is concave down. And the point where concavity changes, and that means the second derivative must change signs from negative to positive or positive to negative. Where concavity changes, we have what's called a point of inflection. Now, the second derivative of a function determines where the function is concave up like a cup, in other words, if second derivative is positive, or concave down like a frown, if second derivative is negative. The point of inflection is the point, x, f at x, where the function is changing from concave down to concave up, or concave up to concave down. At this point, the second derivative will be 0. Concavity must change at a point of inflection. So it is possible for the second derivative to be 0, but for concavity not to change. So that's an important thing to know. If f double prime is 0 for all x on your closed interval a to b, then f is linear and concavity is not defined for a line. There's no curvature. Similar to the method for finding relative extrema, to find points of inflection, we're going to find values for which the second derivative is 0, and these will be possible points of inflection. Very important, possible points of inflection. Okay, so the second derivative is 0 or undefined. So we are going to look at this example here. And we are going to find all the critical numbers and sketch the graph. So first of all, here is my function. We know that f prime of x is going to be 3x squared minus 3. We can factor out the 3, and we see that we have x squared minus 1, which is a difference of 2 squares. So f of x is 3 times x plus 1, x minus 1, and that gives our first derivative 0 when x is negative 1 and when x is positive 1. These are our critical numbers. Now, the next thing we want to do is find possible points of inflection. So from the first derivative, we're going to take the second derivative. And our second derivative is 0 when x is 0. We call this a possible point of inflection. Now, other things that we can do is we can find values on the function at these places. When x is 0, substitute in y is 2. When x is 1, substitute into our function, y is 0. And when x is negative 1, substitute into our function, and we get y to be 4. So here are 3 points we know: 0, 2, 1, 0, and negative 1, 4. So if I just go plot these 3 points, 0, 2, 1, 0, and negative 1, 4. All I know is these 3 points. We have to do calculus in order to learn the shape and direction of the graph. So now we're going to add something in our chart. All right? So we have critical numbers and possible points of inflection, and this is what's going to go on our chart. My critical numbers were where x was negative 1 and 1. My possible point of inflection is where x is 0. We found the y values, and these 3 numbers divide up our number lines so that I am now looking at the interval from negative infinity to negative 1, negative 1 to 0, 0 to 1, and 1 to infinity. And guess what? We are going to test the first and second derivative in each of those intervals. So let's pick a number between negative infinity and negative 1. Why not negative 10? If we substitute negative 10 here, I get 3 times negative 10 plus 1 is negative. Negative 10 minus 1 is negative, so 3 times negative is positive. So the first derivative is positive. While that number negative 10 is in our head, let's go to second derivative, and 6 times negative 10 is negative. So this tells me that f is increasing because f prime is positive, and concave down because f double prime is negative. Now let's go to some number between negative 1 and 0. How about negative 1/2? First derivative. 3 times negative 1/2 plus 1 is positive. Negative 1/2 minus 1 is negative. So I have 3 times a positive times a negative, which is negative. So first derivative is negative. While I have negative 1/2 in my head, let's go over here. 6 times negative 1/2 is negative. So what does this tell me? F is decreasing because first derivative negative, concave down because second derivative negative. Notice that we went from positive to negative on the first derivative. We went from increasing to decreasing, so now we know we have a relative maximum when x is negative 1. Now let's pick a number between 0 and 1. How about 1/2? Again, go through the same process. We get the first derivative to be negative because that's 3 times positive times negative. We get the second derivative to be positive, so now my function is still decreasing, but it's changed shape. So we have gone from a negative on the second derivative to a positive. We have changed signs, so concavity is going to change. We have a point of inflection. Look how we're going from a concave down to a concave up shape. Then we'll pick a number after 1. Why not 10? That's positive times positive times positive. That's positive here, so f is increasing and concave up. And now you can sketch the graph. Now, something very nice. F prime at negative 1 is 0, and f double prime at negative 1 is negative. So this is a really nice way to be able to show that we have a relative max. When we have a horizontal tangent where the first derivative is 0 and second derivative negative. AP really likes this. Now, of course, there is another way to represent this. So I'm going to let you pause and fill in this chart, and then we'll look at, of course, the other way to think about doing this. Same problem, looking at my first derivative function and my second derivative function, doing my test values, notice that I'm going on the whole, all the real numbers. All right, so I pick a number smaller than -1. The first derivative is positive. The second derivative is negative, so I am going to increase concave down. Look at that. And now, from -1 to 0, what did we try? -1/2. -1/2 was first derivative negative, second derivative negative. I am decreasing concave down. Look at that. Picking a number between 0 and 1, we tried 1/2. So substituting 1/2 into here, that gave first derivative negative, second derivative positive. So I am, function f is decreasing concave up. There's a decreasing concave up shape. And then greater than 1, first derivative positive, second derivative positive. So f is increasing concave up. And what's kind of neat when you look at it like this is you kind of see the shape of that function just come out in front of you. You might want to pause and write this down. AP really likes this justification for finding relative maximums and mins. At a maximum, usually that first derivative is 0, and the second derivative will be negative because we're concave down. At a minimum, again, first derivative usually 0, second derivative positive. And you can see at 1, that's what's going on here. First derivative 0, second derivative positive, so we are concave up, horizontal tangent, relative minimum. Now we've really got to get used to using our notation. And so notice f of -2 is 8, f of 0 is 4, f of 2 is 0. These are all giving me points. What does f prime of greater than 0 tell us? It tells us that for all absolute value of x greater than 2, that means all points more than 2 units away from the origin, f will be increasing. This down here tells me first derivative negative for all points where the distance from the origin is less than 2. So all points between -2 and 2, f will be decreasing. All points up to -2 and after 2, f will be increasing. Interesting notation. The first derivative at 2 and -2 is 0. That means we have horizontal tangents. The second derivative is negative for values of x that are less than 0, which tells me when x is less than 0, f will be concave down. The second derivative positive for values of x greater than 0 tells me f will be concave up when x is positive. So if we take all of this information and put it on a little line here, you can see that we have increasing and concave down in this interval. We have decreasing and concave down in this interval. We have decreasing and concave up in this interval, and we have increasing and concave up in this interval. You can see the general shape of the graph. We've got some points, and that's what it's going to look like. There's our point, -2, 8, 0, 4, 2, 0, increasing concave down, horizontal tangent, decreasing, horizontal tangent, increasing. Concavity changing right here. You might want to write this information down and ponder it. Example 3, sketch the curve. So f of x is x to the 4th minus 2x cubed. We are going to have to find the first derivative and the second derivative and find where they're equal to 0. So my critical numbers are 0 and 3/2. My possible point of inflection, second derivative, happens at 0 and 1. And all of those numbers are going to go on our chart. Okay, and you're going to put them in order, 0, 1, and 3/2. This is a critical number, this is a critical number, this is a possible point of inflection. And we're going to do all of the testing in the interval. Okay, so picking a number smaller than 0, try -1, substitute it in your first and second derivative, and we get this result. A number between 0 and 1, how about 1/2? Substitute into the first and second derivative, and we get this result. Take a number between 1 and 3/2. Okay, that's 1 and 1 1/2, maybe 1.25 or 5/4. We get this. and pick a number greater than 3/2, maybe 4. Okay, so you can do it this way. We make our conclusions about decreasing concave up, decreasing concave down, decreasing concave up, increasing concave up, all of these involving F. You can also do the same analysis like this. What is important is you label over here what you're evaluating. For example 4, try number 1 and 2 on your own, and we will look at them in class. Your TPs for 3.4 are 5, 7, 11, and 19. See you next time.